we're diving straight into the second section's video. This next video is about section 2.6, which is function combinations. Function combinations is pretty straightforward. First, let's make up some functions that we can combine. I'll do f of x equals x squared minus, let's do x squared minus 3. And I'll do g of x is x, we'll say plus, we'll go big, x plus 10. So these are two functions. They both have output variables. In this case, the output variable is not a y, it's just an f, and here it's a g. They have input variables, they are equations. Anything you plug in for x is going to give you exactly one output here and the same here. So we have two functions. And we're going to start combining them. Easiest and most simple way to combine these functions is addition. We all know about addition. So let's look at f of x plus g of x. F of x is x squared minus 3. G of x is x plus 10. And if you add them together, all you have to do is combine like terms. So this will give you an x squared plus x plus, looks like I'll get a 7. That's it, we're already done. If we can add functions, then we can also subtract the functions. I'm going to switch the order around. I'm going to do g of x minus f of x this time, see if that changes things. So we'll put g of x first. That's x plus 10. F of x comes next. That's x squared minus 3. Here's the thing you have to be really careful about when you're subtracting these guys. This subtraction distributes. So you have to subtract the x squared, and you have to subtract the negative 3. So when you subtract the negative 3, it's probably going to turn into a positive 3. So if you want to rewrite this as a separate line with a negative x squared and a positive 3, if doing that would help you, definitely do that. I'm going to skip that step. I'm going to skip writing that step. I just talked about it, so I don't know. I probably didn't skip it. I'm just not going to write it. So, keeping in mind that this is distributed and these guys have their signs switched, now I just have to combine like terms. My x squared term is negative. My x term is positive. And my units term is going to have a positive 10 and a positive 3. So that'll be a plus 13 on the back end. That's addition and subtraction. There's all there is to that. If we're going to multiply some functions, f of x times g of x. This still works exactly how you would expect it to work. F of x is x squared minus 3. G of x is x plus 10. When you multiply these guys, you have to FOIL them. So the first term will give me an x cubed. The outside terms is going to give me 10x squared. The inside terms will give me minus 3x. And the last terms will give me minus 30. And then we're done. There's no like terms to combine. Each of these is sort of a different tier term, so that's just it, and we're finished. We can also divide these guys. F of x over g of x. A lot of times dividing these guys is just going to mean you write one on top of the other and then you're done, you're finished, you call it a day. Sometimes you'll have to simplify these things. We'll talk about what that looks like in a second. I'm going to start just by writing these with a division sign. This will be x squared minus 3, that's f of x, goes on top. X plus 10 is g of x, that goes on bottom. And in this case, there's no simplification we can do. The top does not factor nicely, and those factors definitely aren't going to cancel with x plus 10. If one of these things did factor, or if both of them factored, sometimes you can cancel factors from the top and the bottom. You can never ever cancel terms. Like you can't try to cancel this x with one of these x's. That doesn't work. You can only cancel entire factors. And these guys don't have any factors in common, so that's all set. There is one thing we need to add though. We need to say that x cannot equal -10, because now that this thing is in a denominator, it's going to give us a domain restriction. You can't divide by 0, so anytime you have variables in denominators, that's something you need to be careful of. And we can list that as our domain restriction, and then we're done with that. These are the 4 basic operations that we have. The exciting part about function combinations is there are 2 more operations that we can talk about. Well, I guess 1 more operation that happens in 2 different ways. The point is there's more because functions are cool and give us extra options. So I'm going to erase all this and then talk about that. Okay. The extra cool thing you can do with functions that you can't do with most normal numbers is called function composition. Function composition is what happens when you put one function inside of another function. So it's written in 2 different ways. I like to write it f of g of x. I like writing it this way with one big set of parentheses and then something else smaller inside of it because this makes it very clear to me that one of these things is on the inside of the other one. The textbook likes to write this as F-O-G. Looks like fog. This isn't actually an O. It's like it's just like a small circle that gets typeset like in the middle of the line. It's different than an O, I guess. I don't know. It's almost like the degree sign. But the book prefers this way to write it. It's read fog, but it means the same thing. And this is what happens when we take f. This is sort of just like in section 2.1 when we were plugging different weird things into functions. We take f. Here's what f does. F squares something and subtracts 3. So I'm going to square something and subtract 3. This is f. Inside of f, I'm going to put g. G is x plus 10. This is f of g of x. Now I need to simplify. This is not x squared plus 100. Exponents do not distribute over addition. I'm going to say that often. We have to FOIL this. Once you FOIL it, you should get x squared plus 20x plus 100. The minus 3 is going to hang out on the back end. So final answer should be x squared plus 20x plus 97. So this is function composition. This is what happens when you put g of x inside of f of x. We can also do this sort of backwards. We can see what happens if you put f of x inside of g of x. And again, this is how I like to write it. The book is going to write this as gof g of f. So here's what this one does. This one is going to be a little different because g is on the outside. This one's a little different because g is on the outside. So we're going to start with looking at what g does to things. G is going to take something and add 10. So we have something added 10. Inside of this, we're going to put f. So that'll be x squared minus 3. And again, all we have to do now is simplify. X squared minus 3 plus 10 looks like it should be x squared plus 7. That's it. Here's the thing you have to be very careful of in terms of function composition. F of g of x is different from g of f of x. You get very different answers either way. Function composition is not commutative. Commutative is the fancy word we use for operations where the order doesn't matter, like multiplication or addition. So in multiplication and addition, the order doesn't matter. 5 plus 3 is the same as 3 plus 5. 5 times 3 is the same as 3 times 5. These operations are commutative. You can do them in either order and you'll get the same thing. Function composition is not commutative. If you change the order of what goes inside the other piece, you often get very different answers. Sometimes you'll get the same answer. We're going to talk about that a little bit more later. There's some very interesting homework problems in this section where you might end up getting the same answer for f of g and g of f. We can talk about what that means, but not on the video. I am, in fact, done with this video. Function composition, in summary, very straightforward. Addition, subtraction, multiplication, division, all of those things work pretty much how you expect them to work. No surprises there. Function composition is the exciting bit. This is where you get to put functions inside of other functions and see what happens. Oh, I guess there's one more thing I need to say. Sometimes you have to evaluate these functions. And you can do that in two ways. Let's work with this f of g. Let's say I want to find f of g. I already know what f of g of x is. Let's say I want f of g of 2. So this is different now. It's not an x anymore. This is a number. I'm evaluating this at a certain number. And you can do this in two ways. You could start by finding g of 2. G of 2 looks like it should be 12, which means that this should be f of 12. And then you can find f of 12. F of 12 I think should be 144 minus 3. So I think you should get 141. This is sort of like the two-step process. First you find what the inside piece equals, and then you plug that value from g of x into the function for f of x. That's one way to do this. The other way to do this is, we already know what f of g of x is. It's this. So we should be able to just plug 2 into this and see what happens. So that would give me 2 squared plus 20 times 2 plus 97. So let's see what this will work out to be. This will be 4 plus 40 plus 97. The 4 and the 97 should give you 101. And the 40 should give you 141. So, either way you do it, you should be getting the same answer. That's it for this video. Stay tuned for section 3.2.